Okay, welcome to Robotics, ME302. What we're going to do today is this problem right here, which is find the position Jacobian, JP of Q, for the same robotic system analyzed in problem 1, which is right here. This is the A matrix for that, the homogeneous matrix, by deriving the vector O of Q with respect to time. So O of Q. Well, we know that if we have just this matrix, if we're just given this, that this whole chunk right here is the rotational part from B to E. And this part over here is the part that we care about, O, B to E. So this is the O that they're talking about. But actually, you have to take that one step further because this is a small O, so it's not the exact position. It's a ZYZ relative O. So you have to use the forward kinematic solution right here, which is actually the same, basically. You just go ahead and take this O, put it down in the forward kinematic, because this is X, Y, Z, and then phi beta lambda, or phi theta psi over here. So all you have to do is take the partial derivatives of this chunk, and this will give you O of Q, because this is all with respect to Q. So if you're just given this A matrix, you can almost always just grab this part too, if that's the only piece you have. It depends on what you have. But okay, so cranking on with that anyway. So we've got the O of Q that we need to take the derivative with respect to time in order to get the Jacobian. So the basic equation we're working with is d over dt, the derivative of O of Q, and the underlined is vector, is equal to the Jacobian of the forward kinematic position part with respect to Q times Q dot, which is the derivative of Q. So this is actually pretty easy. Don't let this Q dot throw you really, because it's basically just this derivative, the derivative of Q with respect to time. So it's a pretty easy thing, and it won't really matter. The Jacobian is the part you need to care about. So then, looking at the pieces that we have here, what we need to do is create a matrix of each one of these sections with a partial derivative taken with respect to each Q. So we have Q1, yep, this is not working. Let me get my pencil set up again. Okay, so we have Q1, Q2, Q3, and Q4. So we need to set up a matrix using that. The first row will be the derivative with respect to Q1 with respect to time, and then there's so on and so forth moving through there, just taking the partials of it. So to illustrate this, I'll start out with the first one. The derivative of this equation with respect to Q1 will equal negative 2C1 minus S1 of S2 of 1 plus Q3 minus 1. So taking the derivative of S1 gives you cosine of 1. Taking the derivative of cosine of Q1 gives you a negative sine 1. And then the rest of them are considered constant, so you ignore them and it all stays the same. So to show this off again, this is with respect to Q1. Then with respect to Q2, you'll end up with cosine of 1, because sine of 1 is a constant, so constant goes to 0. So you end up with cosine of 1 times cosine of 2 of 1 plus Q3. So we're just taking the partials with this. It's really easy to do. And moving on to the next one with respect to Q3, we go ahead and we end up with cosine of 1, sine of 2. So taking the derivative of Q3, so on and so forth, put that all out, you end up with 1 minus 1, pretty easy. And then with respect to Q4, doesn't have any Q4, so this is all considered a constant, and you get 0. So now I'm just going to crank through the rest of these. 2 sine 1 plus cosine of 1, sine of Q2 of 1 plus Q3 minus 1, and sine of 1, cosine of 2 of 1 plus Q3, and sine of 1, sine of 2, 0, and then 0, negative sine 2 of 1 plus Q3. Cosine of 2, 0. And that is your matrix. This is equal to JP of Q, or JFK of Q, of P Q. So write that down. FK P of Q. Just like that. So that's what this matrix is. So you just take the Jacobian of this matrix right there with respect to each one of the Q's. And that's basically all you have to do. But in order to make it an official answer, you have to deal with this Q dot. So in order to do that, you take this entire matrix, and ironically enough, you multiply it by Q dot. Q1 dot, Q2 dot, Q3 dot, Q4 dot. And that's times this. Times that. Those two are connected right there. And that could be your answer. That would be the complete analytic Jacobian for this matrix. But if you want to distribute it all through and make it even more official, you can go D of dt excuse me, of O of Q is equal to, I'm actually going to move down here because this is going to be really long. Taking the partial, if you take these partials that we defined up here and make them with respect to like Q1 or something like this, if you distribute this Q1 through here, you'll end up with negative 2c cosine of 1 Q dot 1, because you would normally take the derivative with respect to Q1 here, minus sine 1 Q dot 1, sine of 2 of 1 plus Q3, Q3 under there, ignore that little dash, minus 1 plus C1 of C2 Q2 dot of 1 plus Q3, 1 plus Q3, plus sine 2 Q dot 3. And then moving down here, so you see right here, I just took the pieces that we had up here and put in the Q dot, and that's basically all you have to do to show that you actually took the derivative. Very quick, very easy, very clean. And this could be actually your official answer. You cannot use this because this is just JP of Q, but as soon as you multiply this Q dot at the end of it, then it becomes the official analytic Jacobian, and then you can distribute that Q1 dot all the way through and make it official. And this basically shows, well, you took the derivative right here with respect to Q1 and got the answer. So, still pretty easy. Yes, I got all showed all the right stuff there. Yes. Cool. So finishing this out, minus 2 sine 1 Q1 dot plus cosine of 1 Q1 dot sine of 2 of 1 plus Q3 minus 1 plus sine of 1 C2 Q dot 2 1 plus Q3 plus sine of 2 Q dot 3. Then we got negative sine 2 Q dot 2 of 1 plus Q3 plus cosine of 2 Q3 dot. And that is your complete analytic Jacobian. That's your final answer right there, or this could be your final answer up here. So you just take the Jacobian of the O part of your forward kinematic matrix, or the O part of your A homogeneous matrix, and then you multiply it by the vector of Q dot. And that is all you have to do to get the analytic Jacobian.